All right, welcome back for another exciting day of one-dimensional motion here in Physics C mechanics land. All right, so not an April Fool. We're finishing up one-dimensional motion today. All righty then. My name is John Frensley. I teach at Prosper High School in Prosper, Texas, just north of Dallas. For those of you who are tuning in, if you're from Physics 1, about the first half of today might be friendly to what you've experienced. But the second half of today is definitely going to be very Physics C because we're going to dive into some calculus, and that's not for you. All right, so let's start with a warm-up. All right, so last time we talked about representing motion, and we had motions that changed, right? This time I'm going to show you a quantitative example that's dealing with numbers and things like that, but it's going to be another motion that changes. Okay, so I want you to consider the situation. We got a ball that's dropped from rest at the top of a 420 meter tall building, and the ball's terminal speed is going to be 60 meters per second. Now, for the sake of this discussion, I want you to kind of make this algebra based and not calculus based. Those of you in Physics C know that there's a certain way that we analyze these kind of problems of calculus, but we're going to model it differently to make it algebra friendly. I want you to pretend that the ball is going to fall freely for the first however long with like g equals 10 meters second squared, right? Okay, it's going to fall g equals 10 meters second squared until it reaches 60 meters per second. Then the acceleration is going to turn off immediately, okay? So it's not going to be like you've learned. We're going to study actual air resistance next week, but this time we're just going to say free fall until you reach 60 meters per second, then the acceleration just turns off, right? So what I want you to do is using this model where we free fall and then we just have a constant speed, calculate the amount of time it takes for the ball to reach the ground. All right, now remember, you probably need a pencil and a piece of paper and maybe a calculator. You can use a calculator on your phone, but please use g equals 10 and assume that we have that acceleration until 60 meters per second is reached, then a constant downward speed. Here's 3 minutes to calculate it out. On your mark, get set, go. right, the music was a little bit shorter than the timer. We'll give you all about 20 more seconds. This is just a reminder, if the music is not doing it for you while you're doing your little practice bits, then feel free to mute your machine while the timer's running. I promise not to say anything important, and then you can unmute it when the timer reaches 0, and then I'll start talking about real stuff again. All right, all good. Welcome back, everybody. We're going to answer this question a little bit because I'm going to give you a little bit of like me teaching you type time. Okay. So let me give you kind of lesson overview. Okay. I want you to be able to leave this lesson being able to solve problems with the changing acceleration. There are two flavors for that. Now, one flavor is that the acceleration like suddenly changes, kind of like in the warm-up problem where we went from a constant acceleration of 10 to a constant acceleration of 0, like immediately, right? Okay. That's the part that's physics 1 algebra friendly, right? But then you could also have a changing acceleration that changes continuously, and then I have to give you like an acceleration as a function of time, and then that's for C mechanics only, because that's going to involve calculus. So first half friendly for P1, second half not so much. Okay, here's what you need to know about this thing I call segmented motion, right? Segmented motion is when you have a constant acceleration which suddenly changes into a different constant acceleration. It was 10 meters per second squared, now it's 0, for example, right? So we can't model that motion using just one kinematics equation. We have to use multiple kinematics equations, right? We can still use the old kinematics equations for constant acceleration, but you can't just get the answer with one of them. It's going to take more than one, right? So each interval of the constant acceleration is a segment. So in the previous problem, the first segment was free falling at 10 meters per second squared, right? And then the second segment was 0 meters per second squared, constant velocity. I call it a 2-segment problem, right? Here's 3 examples, the first of which was the warm-up, right? Now, when I teach this, I want my students to draw like a timeline. Can you think of it that way, that it's a timeline, right? And they're going to label the timeline with positions, velocities, accelerations, and amounts of time. And that's what's going to help them organize what's going on. So here's an example of what I call a segmented motion diagram. So look at this. This is a segmented motion diagram with 2 segments. So we have one segment here and the other segment there. All right, so this would be an example with 3, right? It looks the same as the 2, but it has 3 segments, right? So let's go back to the 2-segment one because we'll just stay on the 3-segment one here, right? Okay, so what do you see? You see that above each of these vertical lines, there's an X, a T, and a V. These vertical lines are the starting and when the segments change over, right? So this is where you are, what time is it right now, and how fast are you going at the very beginning of the problem. Where are you? What time is it on the clock? And how fast are you going when you stop the first motion and start the second motion? Then where are you? What time is it on the clock? And how fast are you going when you go from the second to the third segment? And then you get the idea. Where are you? What time is it on the clock? And how fast are you moving at the very end? So what would be a 3-segment motion type of problem? Well, the one that you're going to see later is a car accelerating from rest, going constant speed, and then slowing down, right? So where are you? What time is it? How fast are you going when you just get started, when you quit accelerating, when you're just about to start braking, and then when you're done braking, right? Now, on the bottom, you'll see these numbers that tell us about what happens during a segment. So the top numbers are about what's going on when the segments change over. But on the bottom, this delta X, how much distance or displacement did you cover during that segment? So whatever this delta X number is, it's literally going to be the difference between the X at the end and the X at the beginning. So if the final X is 100 and the initial X is 80, then delta X will be 20, right? Same with delta T. How much time did this segment last? So if the final time says 10 seconds on the clock and the initial time says 8 seconds, I have no idea why you would start your clock at 8 seconds, but whatever, then the delta T would be 2 seconds, right? Also note that the acceleration takes place during the segment. So acceleration takes place during a segment, but you start and end a segment with a specific velocity. So let me show you how you apply this to the warm-up problem. Now, I want you to note that you're basically going to solve this like it's a logic puzzle, okay? So what you do is you fill in the blanks that you know just from the paragraph, like the problem that it gives you, and then you use these equations to try and fill in the blanks that you don't know. So you start with all the blanks that you can get just from the paragraph, and then you're going to use your good old v equals ATs and x equal 1/2 AT squares and that kind of thing in order to figure out the remaining blanks. The great unsung hero, in my opinion, of motion is this last equation right here. This is the equation that you can use if something's accelerating. All you have to do is take the average of the initial and final velocity, and then that average of initial and final velocity times the time you spent going from initial to final gives you the distance. And a lot of people don't like to use this, but it's a really good one. You're going to see me use it today. Okay, so the ball is dropped from the rest at the top of the 420-meter tall building. The ball falls until it reaches a speed of 60 meters per second, and then it quits accelerating, right? So first, let's talk about what I know already. I know that we start with a displacement of 0. Let's let the top of the building be 0. Let's let the bottom of the building be 420. It's right there in the paragraph, right? Okay, what else do I know? I know that I'm going to start time at 0, and it says that it was dropped from rest. So I just know that. I haven't done any math yet. Okay, I'm just filling in the blanks that I know. Okay, what else do I know? I also know that I have an acceleration, and it might be a little bit difficult for you to see here at the bottom here, but it says an acceleration of 10 meters per second here at the bottom, meters per second squared, and then the acceleration of the second segment is 0 meters per second squared. And so I apologize if that's cut off from your screen, but that's what's down here, 0 meters per second squared, 10 meters per second squared. Okay. And then what else do I know? I know that the velocity is 60 meters per second at the end of the first segment and stays 60 meters per second. So that's everything I know just from that paragraph right there. Now, this may be very new for you. So if you're watching live, then please expect to go back and watch the rewatch. And if you're watching the rewatch, then you might have to pause and rewind and that kind of thing. Okay, we're going to apply the equations one by one to fill in the remaining blanks. Now, there are multiple ways to fill in the blanks. It's like a logic puzzle, so don't feel like there's just one way. I'm going to show you one way, but there are multiple ways you can fill in the blanks. Okay, so first thing I'm going to do is I'm going to take the fact that I start at 0 position, time 0, velocity 0. I end with 60 meters per second, and I have an acceleration of 10 meters per second squared. I'm sorry if it's cut off on your screen, but it's down here. It says acceleration 10 meters per second squared. And so what am I going to do? I'm going to get the distance I fall during the first segment and the time it takes, right? So I can use acceleration equals delta V over delta T. All right, that's going to get me the delta T. So the acceleration is 10. The delta V is 60. That's 60 minus 0 is the delta V. And so the delta T has to be 6. So it's going to be 6 seconds. Now, how can I get the distance that I go? Well, an easy way to get the distance that it falls is to take the average velocity. So that's 0 and 60, average to 30. Okay, that's the average velocity of this segment times the time. And I just got the time to be 6 seconds. 6 seconds of fall if you fall 10 meters per second squared up to 60 meters per second. So then if I say 30 meters per second of average times 6 seconds, then that's going to be 180 meters. So here's what it looks like right there. That's me getting my 6 seconds. That's me getting my 180 meters. So I fill in my 180 meters in my 6 seconds. Now, here's what I'm thinking. If I start with 0 meters and I gain 180 meters, I must be at a place called, get this, 180 meters. If the clock started at 0 and I spent 6 seconds free falling, then I must now be 6 seconds on the clock now that I have finished free falling, and I'm going to begin a constant velocity for the rest of my fall. Now, look at this. I'm at a place called 180 meters, but I'm going to end at a place called 420 meters, the bottom of the building. So I can get the delta X from that. The delta X is whatever the difference in those two is, 240 meters. Okay, I can't do math. So 240 meters. But now I'm like, hey, if I know that I'm going 60 meters per second constant velocity, and I need to go 240 meters, well, if I just do a little distance equals velocity times time, that gets me 4 more seconds of fall. So now I can finally answer the question. 6 seconds of free falling with gravity equals 10 meters per second squared, and 4 seconds of constant velocity fall. So the final answer to the question is it took 10 seconds for this ball to fall down. All right, all good. So let's take it. So by the way, I want to show you the graphs of this, just so you know, because I always feel like it's important to not just do math, but to always do something pictorial along with the math. So here's the first segment right here. You can see the object going 180 meters in 6 seconds, speeding up to 60 meters per second in 6 seconds, constant velocity of 10. And then you'll see for the red segment, that's the constant velocity segment. So it's a straight line ending at 420 meters. Constant velocity is a flat line at 60 meters per second. And the acceleration graph just drops down to 0 for the last 4 seconds. Okay, all delicious. All right, now it's time for your guided practice. All right, so what are we going to do now? Now we're going to do the opposite. Before it was acceleration, then a constant velocity. Now I'm going to do the opposite to you. It's going to be a constant velocity, then a deceleration. So the car's driving 40 meters per second. That's 90 miles an hour. Please don't actually drive that fast, okay? 40 meters per second. There's a cow up ahead. That tells you about where I live, okay? So there's a cow crossing the road up ahead. It's going to take the driver 1.5 seconds to say, oh my gosh, and then move his foot from the gas to the brake and mash the brake pedal in like there's no tomorrow, because there's not going to be a tomorrow if you hit that cow really hard, right? So if you hit a cow, the cow wins. Let me just tell you right there. Okay, so it's going to take him 1.5 seconds to say, oh my gosh, fully apply the brakes, and then he's going to decelerate. This is a typical deceleration for a car. 8 meters per second squared magnitude. Notice I said magnitude. I'm warning you about that deceleration. Question, how far do you go? What's your stopping distance, right? So first, fill in the blanks that you know based on that paragraph at the top. Then use your basic kinematics to try and link together the quantities one segment at a time. All right, you're going to get 3 minutes for this bad boy. On your mark, get set, go. All right, that's the end of that. All right, I'm looking at myself on the YouTube here, and I'm noticing that, again, the acceleration down here at the bottom has been cut off, and the acceleration down here at the bottom has been cut off. I apologize. So you're going to have to listen as I talk, because I'm going to say what the acceleration is. So let me fill in everything I know. What do I know? First, I know that I start with a distance of 0, because we usually start at position 0. We start at time 0, but this time we start with 40 meters per second of initial velocity. Now, the first segment is about going with a constant velocity while the guy realizes and reacts to the fact that he's in trouble. So I don't know how far he goes, but I do know that that takes 1.5 seconds, and you can't see it maybe, but it's down here. 0 meters per second squared is the acceleration. The acceleration is 0 meters per second squared. Now, I know that if 1.5 seconds elapses after time 0, then the time on the clock now is 1.5 seconds, and I still have my velocity of 40 meters per second, because I have just now begun mashing the brake pedal into the floorboards, right? So now I'm going to be braking. I know I end with 0 velocity, and I know that the acceleration, and I'm sorry again, I can't apologize enough, it's -8 meters per second squared is what's listed at the bottom here. -8 meters per second squared. Why negative? Because the acceleration is directed opposite the velocity. So because my velocity is positive and I'm slowing down, my acceleration is negative. Okay, so I only have a few blanks to fill in. Almost everything just came from the paragraph. Okay, so first things first. All right, I'm just going to use my basic distance equals velocity times time. So the average velocity when you go a constant velocity, it's just the velocity you're going. Listen to that again. The average velocity when you have a constant velocity is just the velocity you're going. So the average of 40 and 40 is 40 meters per second. The amount of time that took was 1.5 seconds. So you go 60 whole meters. That's basically 2/3 of a football field, just realizing that you're in trouble if you're going 90 miles an hour. Please don't actually do that, okay? So now we're going to get to the part where I'm going to slam on the brakes, okay? So I'm going to slam on the brakes. So now I need to figure out how far I go and how much time that takes. So how much time does it take for me to stop? Well, I'm going to use acceleration equals delta velocity over delta time. So the acceleration is -8. Final minus initial velocity is right there. Solve 5 seconds. It takes 5 seconds. It seems like an eternity when you're about to run over a small child or hit another car or a cow when you're mashing that brake pedal, but it's only 5 seconds. So 5 seconds into the future brings me to 6.5 seconds to finally stop. Now I'm going to go ahead and use delta distance is equal to average velocity times delta time. So the average velocity of 40 and 0 is 20. The average of 40 and 0 is 20. There's my average velocity for the second segment. There's the amount of time the second segment takes, which is 5 seconds. So it's 100 meters just to leave tire marks. So it's 60 meters to realize I'm in trouble and 100 meters to leave tire marks. So now we're talking about like 1 3/4 of a football field, or maybe one football field in 80 yards. It's a long distance. So that's why it's important to always pay attention to the road and not be going too fast, right? Okay, here's the graph. What you can see here is the first 1.5 seconds of constant velocity, straight line on a position graph. Constant velocity is a horizontal line on a velocity graph, 0 on the acceleration graph. And then you'll see that the acceleration drops to -8 as the velocity graph transitions to a -8 slope, and as the position graph slopes down to 0 slope as I slow down. All right, all good. Okay, this is the last one. I'm going to give you 4 minutes for it. It's just called green light, red light. So we're going to start from rest. And then when the light turns green at time equals 0, the car is going to accelerate at a modest 2 meters per second squared. It's going to reach 20 meters per second. That's about a major street speed, 45 miles an hour about. It's going to have a constant speed until it reaches the next light up ahead. And then the driver is very close to the next light when it turns red. So he's going to apply the brakes really hard, 5 meters per second squared, because really we don't care about yellow lights anymore. Every yellow light I come across is like 1 second. And why even bother having them? All right. So, okay. So the two lights are 260 meters apart. So the question is, how long does it take to go from the first green light to the next red light? All right. So here we go. Fill in everything you know, and then try to logically deduce your way to the rest of it. All right, here we go. 4 minutes on your mark, set, go. give you all about 10 more seconds. Wrap it up. See what you're able to do here. All righty then. Okay, so let's start with what I know. What do I know? I know I'm going to start with position 0 at time 0 with velocity 0. Start at rest. Time starts when I start carrying, and we start at position 0, right? I know, and I know it's cut off, I'm sorry. I know that the acceleration for this first segment, it's at the bottom, it's right underneath this delta t. The acceleration is +2. I know that this acceleration is 0. I know that this acceleration is -5 because I'm moving forward but slowing down, right? Okay. And then I know I'm going to end with 0 velocity. And I know that I'm going to end with a distance of 260. And I also know that the velocity that I speed up to and I slow down from is 20 meters per second. So now you're going to see all that right here. So I know where I start, where, when, and how fast I start. I speed up to 20, go constant speed to 20, slow down to 0. I end up 260 meters away. My first acceleration is 2. It's hard to see, but it's there. It's right underneath the delta t. A equals 2 meters second squared. A equals 0 because I'm not speeding up or slowing down. And then A equals -5 meters second squared, right? So now to figure out how much time this took, I'm just going to go through the motions. I'm going to start at the beginning and just keep working all the way to the end. So here goes nothing. All right, first things first, I can use acceleration equals delta V over delta T in order to get the amount of time that this took. So the delta V was from 0 to 20. That's a delta V of 20. Okay, the acceleration was 2. Let's just say acceleration 2 equals delta V for the first segment over delta T. So the delta T has to be 10 seconds. And then what's the next thing I have? I can use delta x equals v average delta t. You might notice that I'm not using v squared equals 2ax or x equals 1/2 at squared. You can use them if you want to. Try it on your own. But those equations are hard for me. Okay, it's so much easier to just do a equals delta v over delta t and displacement equals average velocity delta t. What's the average of 0 and 20? It's 10. The amount of time I just got is 10, so that's 100 meters. So I'm going to say that 0, go ahead 100 meters. I'm at 100 meters now. Time 0, advance into the future 10 seconds. So now I'm at a clock time of 10 seconds. Okay, what's the delta x and the delta t here? Well, I don't know, honestly. Okay, so I'm going to have to do the last segment. Look at this. Now I'm going to do the last segment. So I'm going to do acceleration delta v over delta t. So the acceleration -5, you can't see it, but it's there. The delta v is 20 to 0. That's -20 over delta t. So I'm going to get 4 seconds. This last segment takes 4 seconds. How far do I go while I brake? Well, again, I'm going to take the average velocity. So the average of 20 and 0 is 10 times the time that the last segment took. That's 4. So that's 4 seconds. So I found out the distance and time of the last segment. Now, get this. If the first segment is 100 meters, the last segment is 40 meters, and the total distance is 260 meters, then by golly, by gosh, the middle segment has to be the remaining 120 meters. You see how you're logically solving this out. So I'm going to go 120 meters in the middle segment. Well, the 120 meters is going to be spent going to 20 meters per second. So if I go 20 meters per second, the 120 meters of the middle segment, then that's 6 more seconds. So I spend 10 seconds speeding up, 6 seconds going constant speed, 4 seconds slowing down, 20 total seconds for my journey. 20 total seconds for my journey. Okay, so this is going to bring to an end the part that's friendly for AP Physics 1. Okay, let me just show you the graphs really quick. Okay, so here's the speeding up bit, then here's a constant speed, then there's the slowing down bit, right? So we speed up to 20 meters per second, takes 10 seconds, constant speed of 20, slow down over the last 4 seconds, right? Back to 0. The acceleration's 2, then 0, then -5. It might be hard for you to see that -5 acceleration. And I go 100 meters, then I go further to 220 meters is where I am. Then I end at 260 meters. All right. All good. Okay, so now is part for the calculus, okay? So let's go ahead and just remember all the calculus stuff. So we have to do this whenever acceleration is given to us as a continuous function of time, not in constant acceleration segments like AP Physics 1, but they do that sometimes on Physics C as well, so just be warned. But Physics C might also involve calculus. So let's just go through, we know it already. Velocity is the derivative of position with respect to time. That's what WRT means, is with respect to. So velocity is the derivative of position with respect to time, and acceleration is the derivative of velocity. Okay, I hope that this is all old hat for you. If you take the integral of velocity with respect to time, then that gives you how much your position has changed. Not where you are, but how much your position has changed. All integrals give you a change. So the integral of acceleration with respect to time is velocity, how much your velocity has changed. Now, let me just tell you my experience. Students can knock derivatives out of the park, okay? So with your permission, I'm not going to spend the rest of our time looking at derivatives. I'm going to spend the rest of our time looking at integrals, okay? So I'm going to make you take some integrals here in a moment. So I want you to suppose that you have an object. It's at position 0, velocity 0, time 0. We're starting with all zeros, position, velocity, time 0. It's going to have an acceleration according to this graph. So let me tell you what the graph looks like. It's a parabola. I think you can see the parabola part, and it says the function of that acceleration, and then the acceleration is 0 after that, okay? So the acceleration is this parabola, then 0 after that, right? So I want you to tell me the time at which the acceleration turns off, then the final velocity attained by the object after it's accelerated, then the distance that the object is gone. So that's going to be a little algebra, an integral, and then another integral, all right? So here's 4 minutes to do it. On your mark, get set, go. All right, I'm going to show you the solution here. If I go too fast, then you might want to go back to the rewatch, pause, rewind, and take it in a step at a time. So first, the time at which the acceleration quits, we're just going to set the acceleration function equal to 0. So I multiply by 3 in order to clear the fraction. It's not my friend, fractions, right? Factor out a t, and then you know the algebra here. It's either t equals 0, that's when the acceleration starts, nobody cares. T equals 6, that's when the acceleration ends. That's what the answer to the first bullet point was, right? Now, how do I get the velocity? All right, so to get the velocity, what I'm going to do is I'm going to integrate the acceleration. Okay, so here I go. V is the integral of a with respect to time. So you can see my terrible typesetting thanks to Microsoft PowerPoint, but you can see me trying to do an integral from 0 to t. Now, let me just tell you, on the AP Physics exams, they're not going to worry if you use the same variable in your integrand that you have in the limits, but the AP Calculus people will. So I actually changed the t to a different letter, tau, just for a dummy variable is what it's called. And so I'm going to integrate from 0 to t, that's time, but the tau is my dummy variable. So what's the antiderivative of this? The antiderivative of 2t is t squared. The antiderivative of 1/3 t squared is t cubed over 9. And now I'm going to plug in the limits t and 0. I'm going to plug in the limits t and 0. Plug in 0, you get 0. Plug in the limit t, and you get t squared minus t cubed over 9. Now that's the velocity as a function of time. I'm going to need that for the last bullet point, okay? But for the second bullet point, I'm just going to plug in time equals 6. So how fast do you go when acceleration quits? Plug in time equals 6, and you get 12 meters per second. Okay, all good. But how do I figure out the distance that the object's going to go? Well, now what I need to do is I need to integrate the velocity. So here's my velocity function, t squared minus t cubed over 9. It's really tau because it's a dummy variable, right? With respect to time. I'm going to again go from 0 to time t in order to get a function of t. So when I integrate t squared, I get t cubed over 3. T cubed integrated is t to the 4th over 36. Remember, raise up the power, divide by the new power, right? So plug in 0, don't get anything, plug in t, and you get exactly that function. That's the position as a function of time. So then what am I going to do if I have the position as a function of time? What I'm going to do is I'm going to plug in the time equals 6. When I plug in the time equals 6, I get 36 meters. Okay, was that good? Because you get one more example. I'm going to give you 5 minutes on this example, so we might run up to about 50 minutes after the hour. I hope the College Board and you forgive me, but here it goes. It's the same process, except a different acceleration function. And this one has symbols. So when you finish, you're going to have A and capital T in your answers. The acceleration is 1/2 capital A, a constant, 1 minus cosine, 2 pi T, the variable for time, over capital T. So you're going to give me the final velocity in terms of capital A and capital T. You're going to give me the distance that the object traveled while accelerating from capital A to in terms of capital A and capital T. Please note that the acceleration finishes at time capital T. Okay, so here's your 5 minutes. Soak it in on your mark and set go. All right, it's going to be the different integral, but the same process here. So same process. You want to get velocity, integrate acceleration. This time the integral is going to be of this acceleration function. Again, I replaced the t's with tau because you're not supposed to have t in the variable, in the integrand, and in the limits, right? Okay, so I'm going to factor the 1/2 a out of the integral. Now I'm going to take the antiderivative. The antiderivative of 1 is t. The antiderivative of negative cosine is negative sine. But watch out, when you take the antiderivative of cosine, it's going to poop out this little t over 2 pi, which is a result of the chain rule, okay? You could do substitution if you want to, but I'm running up against the clock here. You're going to have to show that substitution yourself. So if you plug in time equals 0, then the t is 0 and the sine is 0. Plug in the little t and you get your velocity function, 1/2 a, t minus this thing that came from the chain rule, sine 2 pi time over capital T. So if I plug in capital T, which is when the acceleration ceases, then everything that's underlined is going to be 0 because the sine of 2 pi is 0. The sine of 2 pi is 0. That only leaves you with 1/2 at. Man, all that calculus, and we just ended up with 1/2 at. It wasn't even that complicated an answer. I know that. I know. Okay, so now we're going to take our velocity function. We're going to integrate it to get position. This is going to look a lot uglier than it actually is. The integral of t is 1/2 t squared. The integral of negative sine is positive cosine. But now we're going to have another one of these t over 2 pi's come out from the chain rule. Again, if you have to do substitution in order to show that, then you have to do u substitution u. Okay, so let's see. Let's plug in 0. If I plug in 0, watch out. If you plug in 0, then cosine is going to give you this t over 2 pi squared. That's the result of plugging in 0. That's the fundamental theorem of calculus. This is the result of plugging in lowercase t. Okay, all good. So then if we plug in capital T into lowercase t when the acceleration ceases, you get all this stuff. And it turns out that everything that I'm underlining right now is going to wind up being 0. The cosine of 2 pi is just 1. So you get t over 2 pi squared minus t over 2 pi squared. That cancels. And only these two things survive. So then you just wind up with these two things canceling and you get 1/4 at squared. Wow, all that calculus work. And we got this simple little answer. Yes, you worked really hard and you're disappointed at the end. That's basically the story of life. All right, if you need to see it again, watch it on the rewatch, work along with it, pause and rewind. Okay, here's a couple of problems from AP Physics C Mechanics. So take a picture of the screen or just pause it if you're doing the rewatch right. If you're doing the live show, then just go back and rewatch it. But that's what you're going to Google search. And those are the two problems you're going to look for that are really good review problems for this topic. And remember that you're going to be able to look at the scoring guidelines, and that's going to help you understand how the problem was scored and how to answer it, right? All right. Well, I hope you all had fun. I will see you when we do friction next time. Are you excited? I know I'm excited. All right. Well, have a good one, y'all. Here's my outro.